We have discovered that we can add exponents together if their bases are being multiplied, and that we can subtract exponents if their bases are being divided. These two techniques for simplifying exponents are foundational to our work in algebra, but we won't stop here. There is one more property involving exponents that we must look into before we discuss our last type of number that can be found as an exponent. Let's look back once again to our product rule. If we have x times x times x times x times x times x, we learned that we can rewrite these variables using exponential notation, x cubed times x cubed. We then found that we can add the exponents together because they have like basis, x to the 3 plus 3. We also learned that we can do this for several terms. X cubed times x cubed times x cubed equals x to the 3 plus 3 plus 3 power, which equals x to the 9th power. Now let's analyze what we have just seen. We have 3 sets of 3 x's. If we spell it out, we have x times 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 x. Instead of saying we have 9 x's being multiplied together, we're saying we have 3 sets of 3 x's. Let's look at these as 3 like bases of 3 threes. If we think of the 3 bases of 3 x's as the number of times our bases are being multiplied together, then we have found a special shortcut to simplifying some exponents. We have 3 bases, so we are going to treat each of the 3 bases as a single unit and say we are going to multiply the bases together 3 times. This will look like x times x times x cubed. Now let's look at the inside. We need to clean that up. We know that 3 x's being multiplied together can be written as x cubed. So let's do that now. We now have x cubed cubed. How do we deal with an expression like this? It's very simple. We treat it like we would a coefficient outside of a parentheses when we're using the distribution property. In other words, we multiply the outside exponent into all the exponents on the inside. So x cubed cubed becomes x to the 3 times 3, which is x to the 9th power. Remember when we had 9 x's? Here is our definition. For all real numbers a and all integers m and n, a to the m power raised to the n power equals a to the m times n power. This states that if we have a real number being raised to any integer power, and then that same term being raised to another power, we keep the base a and simply multiply the two exponents together. Let's work a few examples. Number 1, 3 squared cubed. Here we show the simplicity of the definition. We are given 3 squared raised to the 3rd power. Using the rule, we have 3 to the 2 times 3, which gives us 3 to the 6th power. This equals 729. Number 2, 3x squared cubed. We have 2 parts in this expression, a coefficient and a variable. Remember that even when we do not see an exponent, there is always a 1 in the exponent place. So using the rule, we have 3 to the 1 times 3 power times x to the 2 times 3 power. This gives us 3 cubed x to the 6th, and we simplify to 27x to the 6th power. Number 3, x squared times y to the negative 1 power, all raised to the 4th power. A negative exponent is present in this expression, which tells us that our answer will have a rational number. We have x to the 2 times 4 times y to the negative 1 times 4. Simplifying gives us x to the 8 divided by y to the 4th. Remember that we don't want negative exponents in our answers, so we take their equivalent inverses. Number 4, 1 over 3x all raised to the negative 1 power. Now we have a negative exponent on the outside being multiplied inward. Not only that, but we also have a rational number now. Just like in the last example, we multiply the outside exponent into all of the exponents inside. This gives us 1 to the negative 1 divided by 3 to the negative 1, x to the negative 1. We use the negative rule and take the inverses, and this simply gives us 3x. Here is a pointer. When you see a number, whether it's an integer or a rational number, being raised to the negative 1 power, you simply take the inverse of the entire thing. Number 5, 3 over 2 all raised to the negative 2 power. Here we have a negative 2. We can use the same idea we used from the last example, but at the same time, don't forget to apply the power rule. Something that I personally like to do is to use the negative rule first. So this gives us 2 over 3 squared. Now we go ahead and use the rest of the power rule, giving us 4 over 9. Number 6, 3 to the negative 1 power divided by 5 to the 0 power, all raised to the negative 1 power. Now we have a 0 in one of our exponents. But let's not jump too quickly. Even though we may already see the answer in our head, it's good sometimes to take our time. Let's first use the power and negative rules to get rid of that negative 1 power. We now have 5 to the 0 power divided by 3 to the negative 1. Notice that I kept the negative 1 on the 3. We only applied the rule on the outside exponent, not the inside one yet. Using the 0 rule, we get 1 over 3 to the negative 1. And now we can apply our inverse. This gives us 3.